Good morning to all of you. In previous sessions, we have seen three properties of Fourier transform. First, we have discussed linearity property. Next, we have seen time shifting and time reversal property. So, today we will be discussing the convolution theorem property of Fourier transform. Okay. So, similar property we have seen in case of Z transform. Right. So, the convolution theorem property of Fourier transform. So again, if we have two discrete time signal, that is x1 of n having Fourier transform denoted as capital X1 of omega and x2 of n with Fourier transform x2 of omega, then the convolution of these two discrete time signal, that is x1 of n convolved with x2 of n, so its result we can indicate it as x of n, as the Fourier transform simply denoted as x of omega. So in Fourier domain, this convolution will be simply the multiplication of their respective spectrum, that is x1 of omega and x2 of omega, respective Fourier transforms, right? So the convolution of two signals in the time domain is equivalent to multiplying their frequency spectrums in the frequency domain, or the Fourier transforms in the frequency domain, right? So we'll just try to prove this property, right? So the convolution of these two signals, that is this convolution x of n, that is nothing but the convolution of x1 of n convolved with this is the operator for convolution, right, star. So the convolution of these two signals, that is x1 of n, x2 of n, is simply as per the convolution formula, n is equals to minus infinity to infinity x1 of k into x2 of n minus k. Okay, so this convolution formula we have already seen when we have discussed the convolution topic, right? So this is the convolution formula, right? So as we know that the Fourier transform of x of n, right? If I am taking the Fourier transform of this x of n, so the Fourier transform of this x of n can be represented as x of omega, right? And the formula for Fourier transform is n is equals to minus infinity to infinity x of n into e to the power minus j omega n. So in place of this x of n, we can substitute this value, which is nothing but the convolution of these two signals, that is x1 of n convolved with x2 of n, right? So I will just rewrite this last equation on next slide, that is x of omega is equals to what we have, n is equals to minus infinity to infinity x of n into e to the power minus j omega n. Okay, so this is as per the Fourier transform formula, and in place of x of n, I can substitute this convolution of signal x1 of n and x2 of n as summation n is equals to minus infinity to infinity. I written n, so it should be k. Okay, k is equals to, as per the convolution formula, it should be k is equals to minus infinity to infinity x1 of k into x2 of n minus k, because we have seen the convolution of x of n, which is convolved with h of n, it will be given as summation k is equals to minus infinity to infinity x of k into h of n minus k. Okay, this is nothing but the output response denoted as y of n as per the convolution formula, right? So this summation variable is k here, so I'll just write out here summation k is equals to minus infinity to infinity. In place of x of n, I'm substituting these values, that is this equation, that is k is equals to minus infinity to infinity x1 of k into x2 of n minus k, right? So x1 of k into x2 of n minus k, okay, into this e to the power minus j omega n will be as it is, so e to the power minus j omega n I will keep as it is, right? So this x2 of n minus k into e to the power j omega n, okay, is as per the time shifting property that we had discussed already, right? So as per the time shifting property, if x of n has the Fourier transform x of omega, right? So this x of n minus k has the Fourier transform e to the power minus j omega k into x of omega, right? So as per this time shifting property, we can simply write down this equation as, I can take this summation k is equals to minus infinity to infinity x1 of k outside this summation, that is n is equals to minus infinity to infinity x2 of n minus k into e to the power minus j omega n, and this summation n is equals to minus infinity to infinity x2 of n minus k e to the power minus j omega n. Okay, so this is nothing but the Fourier transform formula for x2 of n minus k. So its Fourier transform can be simply represented as x2 of omega multiplied by e to the power minus j omega k, right? So here I can write summation k is equals to minus infinity to infinity x1 of k into e to the power minus j omega k into x2 of omega, correct. So this term basically again indicates the formula for the Fourier transform, and as per the formula for Fourier transform, so this is the Fourier transform of x1 of k or x1 of n, right? So in place of n simply there is k value, so its Fourier transform will be denoted as x1 of omega, right? So this can be replaced with x1 of omega, so it will be simply x1 of omega multiplied by x2 of omega, that is nothing but your x of omega. Okay, so this is nothing but the convolution theorem property, right? So as per the convolution of two signal in the time domain, okay, is nothing but the uh, multiplication of their spectra in the frequency domain, and here is the proof of that property, right? So we'll try to solve one example here, and we'll apply this convolution theorem property to get the convolution of given signals. Okay, okay, so here two signals are given, that is x1 of n and x2 of n, comprising similar samples, right? And we have to determine the convolution of these two sequences. So when we are seeing convolution, so there are different methods for identification of convolution, that is tabular method, matrix method, then mathematically or graphically you can identify the convolution, right? In Z transform also we are seeing the property of Z transform to identify the convolution. So here we'll try to identify the convolution by using the Fourier transform, by using its convolution theorem property, right? So again, for identifying the convolution, initially we'll identify the Fourier transforms of these two given signals. Okay, so the Fourier transforms of given signals, that is x1 of n and x2 of n, are, so simply it will be denoted as x1 of omega, right? So it will be summation n is equals to minus infinity to infinity x1 of n into e to the power minus j omega n. Okay, so this n, the limit of this n will be from minus 1 to 1. So because the sample at minus 1 is 1, at origin it is 1, and at 1 again it is 1. So I can take it as n is equals to minus 1 to 1 x1 of n into e to the power minus j omega n, right? So it will be x of minus 1 into e to the power j omega, right, plus x1 of 0 into e to the power 0 will be there, right? Plus x1 of 1 into e to the power minus j omega will be there. So after substituting these values of x1 of minus 1 is 1, so it will be e to the power j omega, right? Plus here it will be 1, right? 1 multiplied by e to the power 0, so it will be 1 plus e to the power minus j omega. So this will be here x1 of omega, and the samples are similar in x1 of n and x2 of n. So your x2 of omega will be again same, that is e to the power j omega plus 1 plus e to the power minus j omega, right? Correct. So as per this convolution theorem property, okay, so as per convolution theorem property of Fourier transform, the convolution x of n of x1 of n convolved with x2 of n in Fourier domain is simply their respective Fourier transforms multiplication, that is x1 of omega multiplied by x2 of omega, right? So I'll directly write here x of omega, which will be equals to simply x1 of omega multiplied by x2 of omega. So we have these two equation, so I'll write it as 1 plus e to the power j omega plus e to the power minus j omega, right? Multiplied by the same equation, that is 1 plus e to the power j omega plus e to the power minus j omega, right? So if you multiply these terms with each other, so you will get the actual equation, right? So initially you will multiply 1 with this complete bracket, so you have 1 plus e to the power j omega plus e to the power minus j omega. Next you will multiply e to the power j omega with 1, so e to the power j omega plus e to the power j omega multiplied by e to the power j omega, so e to the power uh, j 2 omega, right? Plus again e to the power j omega into e to the power minus j omega, so e to the power 0 will be there, right? Plus again e to the power minus j omega multiplied by this bracket, so e to the power minus j omega plus again e to the power minus j omega, e to the power j omega, so e to the power 0 will be there, right? Plus e to the power minus j 2 omega will be there, right? So if you identify the sum of this particular equation, so you have 1 here, right? Similarly to the power 0 will be 1, e to the power 0 will be 1, so 1 plus 1 plus 1 will be 3, right? Plus, so the terms of e to the power j omega is there, right? So e to the power j omega, e to the power j omega, so 2 e to the power j omega will be there, right? So 2 e to the power j omega will be there, plus this e to the power minus j omega, again e to the power minus j omega is there, so it will be e to the power twice e to the power minus j omega, right? And finally the remaining term, that is e to the power j2 omega plus e to the power this one minus j2 omega, okay? So this is what the multiplication is, right? But we are interested in identifying the, so we are interested in identifying the convolution of the given signals, that is x1 of n convolved with x2 of n in time domain, right? So this is nothing but the convolution in frequency domain, where the uh, respective Fourier transform of those signals are multiplied, right? So we have to take the inverse Fourier transform of this obtained multiplication result to get x of n, that is nothing but the actual convolution, okay? So for simplification purpose, I will just rewrite this equation, that is x of omega as the sample at minus 2. Okay, that is n is equals to minus 2 will be this one, right? So I'll write this first sample here, or first sample term here. Okay, so I'll write this e to the power j to omega first, right? Next I'll write 2 into e to the power j omega, so plus, my shoes are there. Okay, okay, so plus there 2 e to the power j omega is there, right? Then there will be sample at origin, right? So that is nothing but 3, where the e power is 0, right? So 3 plus again 2 into e to the power minus j omega, so this will be at n is equals to 1, right? Plus the last term is e to the power minus j2 omega, e to the power minus j2 omega. Okay, so by taking its inverse Fourier transform, what we'll get? We'll get x of n. So x of n is nothing but the coefficients of these terms simply. Okay, so at n is equals to minus 2, the coefficient is 1. At n is equals to minus 1, the coefficient is 2, right? At n is equals to 0, the coefficient is 3, right? Because as per, if you are taking the Fourier transform of this x of n, okay, so this is at origin. So if you are taking the Fourier transform of this signal x of n, so it will be 1 into e to the power minus j omega n, but it is the value of minus n is minus 2 here, so minus minus plus will be there, right? So therefore we are simply writing the coefficients here, right? So at n is equals to 0 it is 3, at n is equals to 1 it is 2, at n is equals to 2 it is 1. Okay, so at n is equals to 1 it is 2, and at n is equals to 2 it is again 1. Okay, so this is nothing but the required convolution result of the given two signal, that is x1 of n and x2 of n. Okay. So this x of n is nothing but the inverse Fourier transform of the x of omega. Okay, correct. So this is the required convolution of, so this is the required convolution of x1 of n and x2 of n, right? Given discrete time signal x1 of n and x2 of n, right? So this is how we can use the convolution theorem property of the Fourier transform to identify the convolution of the given signal. So what we are doing initially, so we are initially identifying the Fourier transforms of the given signals, right? So x1 of n's Fourier transform x1 of omega, similarly x2 of n Fourier transform x2 of omega. Then we have multiplied these Fourier transform to get x of omega, and after getting x of omega we are identifying the inverse Fourier transform of it to get the actual convolution result of the given signals. Okay, so this is nothing but the convolution theorem property of the Fourier transform. So in next session we will be discussing the correlation property of the Fourier transform. So thank you for joining this session.